design of the ZSE Max machine, we have the same ratio inside the barrel screw section of 1.66. And at the same time, the torque density for the machine starting at 40 is all at 15, which means if you run a process at a smaller machine, like at a 40mm machine, and you want to know how much you can get for the same let's look at the residence time distribution in those twin screws. And of course, since we have a segmented screw, here's an example of a standard screw that we have used in this experiment. This is where the material comes in. We have a feed section with high volume in the extruder. Then we compress the material. Here we have kneading sections where we can melt the material and melt it even more. And then mix, again mix, and then here we have the pressure generation section. So this is a standard screw. And now this is a screw for a 1.5 OD to ID ratio extruder. And what we wanted to do is compare the lower ratio, 1.5, to the higher ratio of 1.66. So basically the screw is the same, to just compare the impact of the OD to ID ratio on the product. And then we said, okay, since we're doing the experiments anyway, let's look what happens if we have a increased kneading section, meaning we put more energy into the product. Let's see what happens when we make kneading blocks that are harsher and create more energy. Then we said, okay, let's also see what happens when we use mixing elements instead of kneading elements here. And finally, we wanted to find out what happens if we also get a back conveying element into the screw, meaning it pushes the melt back and keeps the melt inside the kneading sections, meaning with that we have a very high energy input. And we try to compare all those various screw geometries via experiment, and I will show you a little film that explains this a little bit closer. Here you can see the film where we have on the one hand the polymer, and here we have calcium carbonate as a tracer for the residence time. Here we see the process section of the extruder, and here we can see the strands, and we can see that with them getting more and more pink, the calcium carbonate comes into the polymer more and more. Then we pulled the strands off, most of them on the left hand side, but one piece we put, or two pieces of strands we put into another pelletizer and pulled the strands out in order to be able to measure how much calcium carbonate is inside those compounds. And after that we did a study where we measured over the distribution time how much level of compound we have inside, how much level of calcium carbonate we have inside the compound. Let's look at the results. This is our typical residence time distribution curves, and we just measured the coming in of the calcium carbonate. This is why they are pretty much symmetrical. Now let's look at first what happened with the low OD to ID ratio twin screw. Okay, we're getting a call from the president. Okay, good. Here we can see the residence time distribution is rather steep and not very wide. This means we have a pretty good residence time level that stays at the same rate, more or less, but the mixing is not as good, because as wider you get in this curve, you get a better mixing ratio. But what's really important is to see the specific energy input that we have for those lower OD to ID ratio twin screws, which is 0.276 kilowatt hours per kilograms, which is a rate that's typical for a compound, but it's a pretty high rate. So you can already damage compounds with such a rate sometimes. Now let's look at what happened with a machine that has a higher OD to ID ratio, the mass machine. 0